Hi guys, I wanted to talk a little bit about significant figures before we get started on anything else. In order to do that, I'm going to pull up the slides that I presented, that I put up for you guys so that we can take a look at that. And then I'm going to show you a couple of other things, one on your calculator. So we're in sig figs, go us. Why do we talk about sig figs? Why are they important? Well, they're important because it shows us the precision of the instrument that we're talking about. So we're looking at two rulers here. Obviously, this one has less gradations on it than this one does. So we don't have as accurate a number looking at this ruler here as we do over here. We can only guesstimate that this is more than 3.5, less than, or more than 2.5, less than 3. I'd guesstimate somewhere in the 7 to 8 kind of range, but I can't really be sure. If I look over here, on the other hand, even though this is exactly the same size and everything else, we can see that this particular paper clip is not only 2.5, 2.6, 2.7, but it's actually a little bit higher than 2.7. It's closer to 2.7 than it is to 2.8, and so the estimation would be, in my opinion, 2.72. Now, what did I just do there? I took the number that I can read, and I said, okay, fine. I know it's 2 something. And then I did one thing beyond that. So 2.7, 2.71. Okay, so we're estimating that last place, which we don't actually know. That is the expectation, is that you will be doing that for things like this. Now, that's not going to be true on a balance because it's going to give you what it gives you. You can't estimate beyond that. But you can do that for things like milliliters. You know, if we're talking about glassware in the lab, this is mostly lab stuff. You can do it for rulers. Obviously, that works. That's why I'm using it. But some other things like that. Okay, so it is the expectation. And there is uncertainty in that final digit because we don't really know what it is. We're just guesstimating. Okay, same kind of example, except now we're looking at a different ruler. Okay, this one, we know it's more than 20, it's less than 30. Again, it's more than 25. I again would say, I say that looks like close to 28. So that's my guesstimate. If I come over here, again, 25, 26, 27 and some. So 27.2 is again the estimation that I would make. So we can look at all of those things. And we can say that we have a knowledge of that number to a specific number of digits. So in this case, this ruler number, ruler number 1, we know that we have 2 sig figs, 3.7. In ruler number 2, we have 3.72, so that's 3 sig figs. This is a more precise number on ruler 2 than it is on ruler 1, and that's what the sig figs imply to us, is that we know something with more precision. Okay, so there's that. That's why sig figs matter. Now, some other things about sig figs that we need to talk about. How do I know if a number is actually significant? Well, we've got a couple of rules for that. Generally speaking, any number that is not 0 is going to be significant. That's easy. But what about those zeros? Are they always significant? Are they not always significant? What are the rules? Well, any zeros that are between two non-zero numbers. So if we're talking about 101, that 0 in the middle is significant. So I have 3 sig figs. 1001 has 2 zeros in the middle, and that's 4 sig figs. Okay. Now, if the zero's in the lead, erasing can proceed. This is just to help us remember that if those zeros are up in front near the decimal place, then if we were to write this number in scientific notation, we could get rid of the placeholders. That's all they are, placeholders. We can get rid of that using scientific notation. So those numbers are not significant. They are just placeholders. Right? So each of these numbers, 0.01, 0.001, and 01 has 1 sig fig. Okay. What about the zeros at the end of the number? Well, it kind of depends. So generally speaking, if they're at the end of the number, they've been put there for a reason, okay? So 1.0, we know it's exactly 0. That's two significant figures. We wouldn't have put the 0.0 there unless it actually was something that we knew. 1.00, same thing. So 2 sig figs for 1.0, 3 sig figs for 1.00. If we look at 0.010, the 2 sig figs at the beginning, or the two zeros at the beginning are not significant. But the 1 and the 0 at the end, the ones on the right-hand side, are significant. Okay? Fabulous. Now, we always get this conversation about how do we know how accurate some number is when we have it? You know, we're talking about a concert venue and there were 500 people there. Were there exactly 500 people? Or were there 500-ish people? Is that a guesstimate or is it a real number? We take care of that in this way. If there's a decimal at the rear, that's 0 you hold dear. So in the case that we have 100 with a decimal place, all 3 of those numbers are significant. That decimal point indicates to us that we counted exactly 100. So it is precise. Okay, so that's what that decimal place there is. It is not an error. It is there for a reason. Now, if there's no decimal there, we have no idea. It could be an estimate. It could be a precise number. We really don't know. And because we don't know, we can only use that first one as a significant number. Okay, without further information, that's all we can do. Usually, we will report something like that in scientific notation, which will then tell you how many significant digits you have and then how many placeholders you need. So 1 times 10 to the second is 100 with 1 significant digit. So 1 sig fig on this one. 1.0 times 10 to the second is 2 significant digits. Okay. 1.00, 3 significant digits. Okay. So again, we want to make sure that whether we're reporting a number with scientific notation or not, we have the correct number of significant figures. But here's the thing. Often we take our numbers and we do some mathematics with them, right? I mean, we don't usually find numbers in a vacuum. So how did the significant digits play into that calculation? And that's what we're going to look at next. So one more way to look at, again, looking at the rules for the sig figures one more time. Non-zero numbers are always significant. Zeros between non-zero numbers are always significant. All final zeros to the right of the decimal are significant. Placeholder zeros are not significant. And to remove them, we write the number in scientific notation. And then rule 5, counting numbers, 1, 2, 3, out in front of moles, that's typically what we're talking about, that kind of thing. Those are what we would call an infinite number of sig figs. Defined constants are also that way. Avogadro's number, 6.022 times 10 to the 23rd. We do not look at those numbers, those 4 digits that we have, as 4 sig figs. We assume that number is infinitely significant. Okay, so that's where we talk about that. Now, if it's a conversion factor, that's what we're talking about with defined constants. One thing we're not talking about is molecular weights. So how do we know what we're looking at when we talk about molecular weights? Well, that depends. So if you've looked between a couple of different periodic tables, you've probably noticed that these don't all have the same numbers on them. Some have 16.0 for oxygen, some have 15.99999 for oxygen. It depends on what you're looking at, and it really often depends on how many significant figures they're willing to put on that table. Some tables, for simplicity, only use 2 decimal places and then whatever's in the front. So that's just for convenience in presenting that particular thing. It's not a real measure of that accuracy. But if that's all you have, that's what you work with. So if it's 1.01, because this particular periodic table only reports 2 decimal places, then you have 3 sig figs in that number. Okay. Other periodic tables will have more decimals, more precision out there. If it has it, use it. Okay. When we do addition and subtraction with significant figures, okay, Say we have one that has 3 decimal places, one that has 1 decimal place, and one that has 2 decimal places. We're going to add all 3 of those numbers together just like we always do and give us this answer that doesn't take any of that into account. And that gives us 1931.393. Okay, but let's look at the numbers we used to get that. The least precise number is the 189.2. It's 1 decimal place. So that's all the precision that we can have. Just because I used numbers from a more precise instrument doesn't make this number any more precise. It does not. So the only way that I can report this answer is as 1931.4. Okay, so we don't gain precision, and that's why we're looking at where are we in terms of our where are our sig figs, where do they end? So addition and subtraction is how far over is your least significant digit. Okay, multiplication and division. This is a similar situation. We're multiplying 3 numbers here. We have one with 4 significant digits. We have one with 3 significant digits. We have one that has actually 2 significant digits. Okay, fine. We do the mathematics on that and we end up with this big number out here. Okay, awesome. But I can't report that because that indicates 5 sig figs, and I don't have 5 sig figs. The least precise number that I have only has 2 significant digits. So whether I put it in the 0 format or I put it in scientific notation, it's going to be 0.000049 or 4.9 times 10 to the minus 5th. Okay, 2 significant figures for that. All right. Some of the things that we talked about, exact values don't count, and these are typically conversion factors or counting numbers. So 2.54 centimeters per inch, 12 inches per foot have infinite precision. So we're not going to worry about those numbers in looking at our sig figs. We round after calculations. Why am I telling you this? Because look at what we did here, right? Let's just say that we had to multiply all of these numbers and then we had to do some other calculation with it, addition, whatever. We sometimes go through and use numbers multiple times. I can calculate a molecular weight, then I can take a mass and use that molecular weight to convert to grams. Once I've converted to grams, then I can convert to the number of molecules. 3 separate calculations. When I report answers, if I report them for all 3 of those steps, I will report them to the correct number of sig figs for that calculation. When I go to do the second calculation, I want to keep all of the sig figs, all of the numbers that I got from the calculator, so that I can make sure that my answer has very few errors. And that's what we're talking about with the accumulation of error. Now, this assumed 3 sig figs for all values in this class does not actually matter. That is not relevant, so sorry for leaving that there. I wasn't paying enough attention. But that's what we're talking about in terms of those things. This whole thing is here so that you know, keep all the numbers when you do this. Now, what am I talking about when I say that? Well, let's take a look. I'm going to share something on my other screen. This is a way to look at my calculator. Okay, awesome. So I have a calculator. I go 3.24 times 1.9. Oh, wait, turn it on. 3.24 times 1.96. Okay, awesome. And then I'm going to subtract from that 2.56 times 2.48. Notice, even though I only had 2 decimal place, three numbers, 3 sig figs here, I did not limit this number to 3 sig figs. I continue my calculation with all of those decimal points. Now, if I needed to report this, if I got asked what is the result of that part of this, I'd report 6.35. Okay, that's how I would report that. Okay, but we're going to continue the calculation with everything that we have. All right, so that's what we're talking about for that. Now, one other thing I'd like to show you. Let's just say that we're talking about 4.2 times 10 to the third. 4.2 second EE3. That's how we put in scientific notation, okay? We don't put that in as 4.2 times 10 to the third, okay? The reason that we don't do that is that if we do calculations with this, we can end up with a placement error. We end up with an extra zero in different places. If you do it multiple times, you can end up with way too many of those issues. So make sure that you're entering this as scientific notation, otherwise your number may not come out the way it's supposed to be, okay? So remember, again, that's 4.2 second EE and then 2 for that, 3 for that 10 to the third, okay? So make sure you do that way. All right. Now let's continue talking over here, and that means I share it again. It's always helpful. Okay. So let's continue with this. What do we do when we have those calculations? So we did some of these before. We add them together. We go to the least or the closest one to the decimal point. So these are both 49.06, 12.74 were both 2 points past the decimal. So that's what we're going to have in the end. Now, why am I showing you the rest of this? Well, it's talking about this uncertainty. So you know that looking at this number as reported, it could have an error of 0.05. So it could be that we estimated that last thing, and it could be, higher or lower than that, and we estimate that as half of that last place. Okay. When we add those two together, those uncertainties, that gives us a 0.1. Now, I don't care that you care about that part. I just want you to see that those numbers have uncertainty in them. This is how we get propagation of errors. Okay. So we have to make sure that we're using as many numbers as we can when we're calculating things before we do the rounding. All right. That's the whole purpose of this slide. Okay. Now, rounding. Ooh, we talked about rounding. Yes, we need to do this, but I already know how to do this, right? Not so much. Parts of it, yes, but there are additional rules that we use when we're talking about sig figs that you don't normally use. So if I have a number, 56.87, that I want to round to the first decimal place, my last digit is 7, so I should round up to 9. Okay, awesome. I can do that. That's rounding up. 12.02, and I need to round it to the first decimal place. This number being less than 5, we round down, 12.0. All of that is just as we've always done it, okay? If I have a 5, that's where we come into this weirdness, because we talk about above 5 or below 5. At 5, we start seeing some differences. So when this number here, the number after the one I need to round, is 5, then I have to look at what's after that. If there's anything that's not a 0 after that, then we're going to round up, okay? So we're going to take this 5, that rounds this to 7, 9, okay? If it's a 5 and it's not followed by a non-zero digit, what do we do then? Oh, Lord. Well, if there's nothing after that, the implication being that it's all zeros, we have to look at the number before it. So 2.835, we're talking about what does that 3 look like? And what I care about is 3 even or is 3 odd? If 3 is odd, then I will round up. So 2.84 is my result because I've rounded 3 up because of the 5 that's after it. And 5 and no zeros, okay? But that's all because it was a 3. If, on the other hand, we're talking about a situation where we have 2.65, okay, and we're going to round this, since there's nothing after the 5, I have to look at the 5. What's the number before it? That number is even. I'm going to round down to 2.6. Now, why do we do that? Well, it's supposed to all come out in the wash, is the way that we talk about it. Everybody has particular bias that they use when looking at numbers. Some people prefer odd numbers versus even numbers. Some people always add, some people always subtract. We want to avoid that bias. So that's why we use the system that we have here, so that the odd numbers always go up, the even numbers always go down, and in the end, it should all come out in the wash, okay? So that's why we do what we do, and those are the rules that you need to use. Is this going to come up a lot? It can. So when you're doing significant digits and you're reporting those things, it may be an error 1 in ALEKS. You may see it as an error when you're doing work in ALEKS. And you may see it as something that you've done wrong on a test. If it's done wrong on a test, it's a very minimal problem. Okay, so if it's a 20-point question, you're not going to lose 20 points for rounding wrong. You're going to get a notification that you rounded wrong and a reminder to go look at the rules again so that you can see how that's supposed to work. That's all that is. Okay, so it does come up, occasionally crawls into tests. It may or may not be intentional that it's there. Okay, questions, comments, problems. I know you're not here, so you can't say that you have questions, comments, or problems. But if you do, if you have anything that you want to talk about based on the information that's in this lecture, take a note of which lecture it is, i.e. the SigFig lecture, the approximate location of that, i.e. give me the timestamp for it, and then what is your question, comment, or problem. And if you can submit that to me via email or in my office hours or whatever, then we can talk about why I said what I said, and I can provide clarification, okay? So I hope that helps you guys with the significant figures. We do need to pay attention to them. You'll notice that we pay a lot more attention to them in the beginning to try and make sure that you have the rules and you've beaten this into your head. Once we think you've beaten it into your head, we'll stop paying as much attention to it, but it will still be present, okay? So I hope that helps. And I will go ahead and post this in a couple of minutes, and good luck.